Welcome everyone to our deep dive into the world of proxies, specifically a showdown between reverse proxies, API gateways, and load balancers. In today's highly distributed and scalable system designs, understanding these foundational components is absolutely crucial. They are the unsung heroes that sit between your users and your application servers, playing pivotal roles in performance, security, and reliability. Often their functionalities overlap, leading to confusion, but each has a distinct primary purpose. Over the next few minutes, we'll peel back the layers, clarify their individual strengths, discuss their commonalities, and explore how they integrate into modern architectures to build robust, scalable, and secure applications. Get ready to demystify these powerful network intermediaries. Before we pit our contenders against each other, let's establish a common ground. What exactly is a proxy? In simple terms, a proxy server acts as an intermediary for requests from clients seeking resources from other servers. There are two main types, forward proxies and reverse proxies. A forward proxy sits in front of clients, forwarding their requests to external servers, often used for privacy or accessing blocked content from within a network. Think of it as a client-side agent. Our focus today, however, is on the reverse proxy. Unlike its forward counterpart, a reverse proxy sits in front of one or more web servers, intercepting requests from external clients and forwarding them to the appropriate backend server. It's a server-side agent, enhancing control and capabilities for the application provider. Let's delve deeper into the reverse proxy. Its core function is to act as a single point of contact for external clients accessing a set of internal servers. Beyond simply forwarding requests, reverse proxies offer a suite of powerful features that significantly enhance server capabilities. These include load balancing, distributing incoming traffic across multiple backend servers to prevent overload and ensure high availability. They also provide a crucial layer of security, shielding backend servers from direct exposure to the internet and filtering malicious requests. Caching static content is another common function, reducing the load on application servers and speeding up content delivery. Furthermore, reverse proxies often handle SSL/TLS termination, decrypting incoming HTTPS requests and forwarding them as HTTP to backend servers, simplifying certificate management and offloading CPU-intensive encryption tasks. While reverse proxies can offer basic load balancing, the dedicated load balancer takes this function to a whole new level. Its primary mission is singularly focused, efficiently distributing incoming network traffic across a group of backend servers. This ensures no single server becomes a bottleneck, maximizing throughput and minimizing response times. Load balancers are critical for achieving high availability and scalability, allowing applications to gracefully handle sudden spikes in traffic. They employ various sophisticated algorithms, such as round-robin, which distributes requests sequentially, or least connections, which sends new requests to the server with the fewest active connections. Some can even perform health checks on servers, directing traffic away from unhealthy instances, further enhancing reliability. Moving up the stack, we encounter the API gateway, a sophisticated management tool often associated with microservices architectures. While it can include reverse proxy and load balancing capabilities, its role extends far beyond. An API gateway acts as a single entry point for all API calls from clients, routing them to the appropriate microservice. More importantly, it provides advanced API management features. This includes authentication and authorization, verifying client identities and permissions before forwarding requests. It also handles rate limiting, protecting backend services from abuse or overload by restricting the number of requests a client can make within a certain time frame. Furthermore, it can perform request transformation, data aggregation, and even introduce policies like caching at the API level. It's an orchestration layer for your API ecosystem. Now that we've explored each component individually, let's put them side by side and highlight their core functional differences. The reverse proxy, at its heart, enhances the security and performance of backend servers by acting as an intermediary, handling SSL termination, and providing caching. The load balancer's core function is pure traffic distribution, ensuring high availability and optimal resource utilization across a server pool. The API gateway, however, operates at a higher application level, providing comprehensive API management. It's concerned with client-specific policies, microservice routing, authentication, and data manipulation. While there's some overlap, for example, an API gateway might include load balancing, their primary responsibilities guide their optimal use cases. Beyond functionality, understanding where these components typically sit in an architecture and their scope of management is key. A reverse proxy generally operates at the network or transport layer, layer 4/7, directly in front of web servers or application servers, managing HTTP/HTTPS traffic. Its scope is typically focused on protecting and optimizing a group of backend servers. A load balancer also operates at similar layers, layer 4/7, but its placement is specifically to distribute traffic to a farm of identical servers, ensuring even distribution and fault tolerance. Its scope is purely about traffic routing and server health. The API gateway, on the other hand, operates at the application layer, layer 7, and is positioned in front of multiple different services, especially within a microservices ecosystem. Its scope is much broader, managing not just traffic, but also API contracts, user identities, and cross-cutting concerns across various services. Deciding which component to use often depends on your specific needs. If your primary goal is to secure and optimize a single or small group of backend web servers, handling tasks like SSL termination and caching, a reverse proxy is your go-to. If you're building a highly available and scalable application that needs to distribute incoming requests across a pool of identical servers to handle high traffic, then a dedicated load balancer is essential. Finally, if you're managing a complex microservices architecture with numerous APIs requiring advanced features like authentication, rate limiting, and sophisticated request routing to different services, an API gateway is the most comprehensive solution. Often, these tools are not mutually exclusive and can be combined for optimal results. The most powerful and common architectural pattern in modern systems is not choosing one over the others, but strategically combining them. It's often beneficial to use a load balancer in front of reverse proxies, which then front your web servers. This setup allows the load balancer to handle initial traffic distribution and health checks, passing requests to healthy reverse proxies. The reverse proxies, in turn, can manage SSL termination, caching, and basic security for the underlying web servers. When integrating microservices, an API gateway typically sits at the edge, acting as the single entry point. Behind the API gateway, you might find load balancers distributing requests to multiple instances of each microservice, or even reverse proxies in front of specific service groups. This layered approach creates a highly robust, scalable, and secure architecture. In conclusion, reverse proxies, load balancers, and API gateways are all critical components in building highly scalable and resilient systems, each with a distinct primary role. The reverse proxy primarily shields and optimizes backend servers. The load balancer ensures efficient distribution of traffic for high availability. The API gateway acts as a powerful orchestrator for microservices, managing API contracts and client interactions. Understanding their individual strengths and how they complement each other is essential for effective system design. As cloud-native architectures continue to evolve and complexity increases, the strategic combination of these tools will remain a cornerstone of robust, performant, and secure application delivery. Always evaluate your specific needs, traffic patterns, and architectural style to make informed decisions.